Okay, so for the second unit or second chapter, we will go into the topic of nomenclature of organic compound. So the word nomenclature is basically is on naming. Okay, we'll try to learn on how to name the organic compound, and also if the name has been given, we should be able to draw back. So the objective or the outcome for this unit, the first is that you should be able to explain the rules of nomenclature for this organic compound. And second is to describe the nomenclature of organic compounds, given that if a structure is given, you should be able to name it, or if the name is given, the name of the compound is given, you should be able to draw the structure. So it's vice versa. So before we go into the nomenclature part or the functional groups of the organic compound, what is an organic compound? So this actually falls under the organic chemistry unit or the branch. Okay, like in chemistry, there are five main branch that falls under the chemistry. One is the physical chemistry, and then you have inorganic, then we have organic analytical chemistry, and also biochemistry. So in organic chemistry, the relevance or why you as a pharmacy student or as a pharmaceutical science student needs to learn or need to know about organic chemistry is most of the compound or the products or the active pharmaceutical ingredient that is available in the drug formulation are made out of organic compound, okay, which is carbon and hydrogen basically. So either some of them may be synthetically made, or they are available naturally in plant or probably in animals. So that is why as a pharmacy or pharmaceutical science student needs to know, especially on the organic chemistry part. So what is an organic compound actually? So it is a molecules, okay, that contain carbon atoms that covalently bonded to the hydrogen atom, which is CH. So here the structures of the carbon and hydrogen are being represented in this electron shell. Okay, you have your hydrogen with the s orbital. Okay, this is s orbital, s orbital. The s orbital shape is basically just round, while the carbon is in the p orbital. Okay, you have p here and then another one and this one. So these are all covalently bonded between carbon and this carbon, or between carbon and this hydrogen. If there is only just one carbon available, so like CH4, so that will only this carbon will have another covalent bond or sigma bond with another hydrogen. So basically, if you see any compound that contain carbon and hydrogen, so it is most definitely an organic compound. Okay, so this is another example or representation. Some of it may also contain a heteroatom, such as oxygen, nitrogen, sulfur, and even you can also have halogen from group 17, like chlorine, bromine, iodine, or fluorine. Okay. So these are, I've listed here like some of the differences in which that you can see between organic and inorganic compounds. Like for most organic compounds, they have low melting, low boiling point, and also some might be have low solubility in water. Whereas in inorganic, they have high melting, high boiling point due to the fact that most of them will contain metal in it. Okay, if you see any compound like for example iron sulfate or copper chloride, so those are considered to be as inorganic compound. So when you have uh, metal in the structures of the compound, so there's a probability that the melting point or boiling point could be higher. And then this is in terms of solubility, high solubility in non-polar solvent, but this actually depends on types of organic compound itself. If the compound is non-polar, then most definitely it will prefer to be soluble in non-polar solvent. And flammable, yes, being an organic compound, most are flammable. So if you go into the lab, make sure that you see on the label on each container. So there will be a symbol like a fire symbol. So that is the symbol for being a flammable material. And then the solutions are non-conductor of electricity because this is due to reason that the organic compound, when you mix it in water, it won't dissociate like in organic. Let's say if you have copper chloride, if you mix it in water, it will dissociate into copper 2 plus and chloride ion. So those ions actually helps in terms of electricity conductivity. Okay, and they also exhibit covalent bonding and isomerism, and their chemical reactions are usually slow, which is true because the reaction sometimes can have the time of like maybe 24 hours or maybe 48 hours depending on the type of the reaction itself. Okay, the shortest could be from 1 hour or maybe half an hour. Unlike in inorganic, chemical reaction can happen instantaneous. Once you mix, you can immediately see changes or product form. But in organic reaction, it will require some time in order for the reactions to proceed. The importance of organic chemistry. So why you as a pharmacy student needs to know about it. One is because that it relates to the drug formulation itself. But then again, these are actually closely related to our daily life. Okay, which is one thing is food. Food itself contain a lot of organic compound. The three main groups, which are proteins, fat, and carbohydrates, when they how to say being become the most simplest form, they are actually an organic compound like in protein. Okay, protein, so this is the structure of protein being represented in ribbon form. So the simplest form of protein would be amino acid. Okay, amino acid actually contain carboxylic acid and also amino group. And fats, which is this, okay, can be divided into saturated and unsaturated fat, which is actually fatty acid. Okay, they are actually carboxylic acid. Okay, so the acid part, and why it is known as fatty acid, because this non-polar, a very long non-polar chain over here. So that's why they are known as fatty acid. Okay, and this is unsaturated. Unsaturated just because there is a presence of C double bond C over here. So saturated, no double bond anywhere you can find. But for unsaturated, you have this C double bond C. And carbohydrates, when it becomes the simplest form, uh, it can be, you can actually see that it is actually having these so-called like cyclic structures, which is glucose and also fructose. Okay, when these two combine together, they become sucrose, which we call as a disaccharide. So saccharide refers to the sugar itself. Di meaning you have two. In this case, there are two different types of sugar, which is glucose and also fructose. So these are just some example of how you can find organic chemistry in our daily life. In fact, other examples can be from like plastic material, which is made out of polyethylene, which is actually an ethylene undergoes polymerization reaction. Okay, like styrene, those container that you use to pack food, polystyrene. Okay, the styrene structure is actually an organic compound, to name a few. Even our clothes, which are made out of polyester, so they are actually made out of ester. Okay, ester, which is a functional group that is under the organic compound and undergoes the polymerization process. So that's how, if you want to relate organic chemistry in our daily life, okay, in human lives. So the classification of organic compounds, how the organic compound are being classified. So they are mainly what we call as hydrocarbons. The hydrocarbons contain hydrogen and also carbon, hence the name hydrocarbon. So they are divided into two main groups, which is aromatic and aliphatic. So aromatic hydrocarbons, the example used here is benzene, and you can also have heteroaromatic hydrocarbons like this pyrrole, furan, typhene, and so on. So the word hetero refers to this heteroatom, which is N, O, and S, okay, nitrogen, oxygen, and sulfur. But being this cyclic form, it still maintains its aromaticity. So this part, the aromatic hydrocarbon mostly will be covered in next semester, okay, in your organic chemistry too. But the aliphatic, so they can be further divided into saturated, saturated, which is alkene, doesn't contain any double bond or triple bond, and it can also be classified under unsaturated, which is alkenes, contain double bond, or alkynes, okay, which contain triple bond. And these are, all of these three open chain or straight chain, meaning that they are not in a cyclic form. Okay, whereas for cyclic, they falls under another category which we call as cycloalkanes, or it can also be cycloalkene and so on. Okay, so open chain or straight chain, and you can also have the cyclic form. Okay, but this is, all of this is without any other functional groups present. Okay, so what are functional groups? So functional groups groups or atoms that are attached to the molecules. So these atoms or group of atoms will give different characteristic to that particular organic compound, and hence they will behave differently in chemical reaction. So they are attached to the carbon backbone, okay, of organic compound or organic molecules. So let's say over here we have a few examples. So R, which are all of these examples, represent the hydrocarbon portion to which the functional group is attached, being that R, the simplest form is CH3, okay, which is an alkyl group or methyl group. So you cannot have R as hydrogen. If R is hydrogen, then this is not an organic compound anymore. So the simplest could be CH3. Okay, so the first functional group would be alkyl halide. So if you have halogen attached to the carbon over here, so it will be known as an alkyl halide, or also haloalkane. Okay, so RX, X refers to fluorine, chlorine, bromine, or iodine. Okay, fluorine, chlorine, bromine, or iodine. So it will be called as an alkyl halide. And this functional group over here, which is the halogen will be known as halo. So you do not call it as fluorine, methane or something like that. It will be known as fluoro, chloro, bromo, and also iodo. Okay, later we will see under the subtopic of alkyl halide. And then the second would be alcohol. So this, if you have an OH group attached, okay, to the carbon backbone. So if you have this OH or hydroxy group, so it will be known as alcohol. And then you have ether. Ether, the general structure will be ROR. So the oxygen is in the middle with single bond on both sides. So these are known as alkoxy group, which is OR. Okay, this either one of these OR is known as an alkoxy group. And amine. So amine, if you have the NH2 or R2NH, or in fact, all of the hydrogen is being replaced with R group or alkyl group, also it is possible. So R3N. So as long as there is nitrogen found to be forming a covalent bond with a carbon, so that falls under amine. Okay, like this example, this NH2 is attached to this methane. So this NH2 is known as an amino group. Okay, amino group. And then you have thiol. Okay, thiol is when you have the R or the carbon backbone attached to a sulfur and hydrogen SH. So this is known as mercapto group. Okay, but the type of compound is known as thiol. And then for sulfide, you have RSR. So this is similar like to ether. Okay, all single bond, single bond. And the SR group is known as alkyl thiol group. Okay, alkyl thiol group. And then you have the aldehyde and ketone. These two contain carbonyl group, which is C double bond O, but the position of where this carbonyl group is present. For aldehyde, it is at the terminal end, which is the last carbon. Okay, you have C double bond OH, and only on one side you have the R group. Okay, example here you have CH3. But for ketone, okay, the carbonyl group will be bonded to two R group or two carbon on both sides. So this side also you have carbon, and on the right side also you have carbon. So like this example, you have CH3 and CH3. And then we go to carboxylic acid. So this one you have R with C double bond OOH. So the functional group is known as carboxy group, whereas the compound is known as carboxylic acid. And for ester, so these three ester, amide, and acid chloride are actually the derivative of carboxylic acid, meaning that from carboxylic acid, it can be converted into ester, amide, and acid chloride, depending on the type of reagent that you mix it together. So in ester, the hydrogen part over here is replaced with another R group. Okay, the R doesn't have to be necessarily the same. So this could be different R group. This could be another R group with different carbon chain length. Okay, let's say you have CH3 over here. On this side, there could be more than one carbon. It can be 3 carbon, CH2, CH2, CH3, for example. Okay, so the functional group is C double bond O, OR, which is this one, C double bond O, OR. And then in amide, so in amide from carboxylic acid here, the whole OH are going to be replaced with either NH2 or NHR, or in fact you can have NR2 as well. So the functional group depends. It can be C double bond O NH2, NHR, or C double bond O NR2. And over here we have the acid chloride. So in acid chloride, the OH, okay, the whole OH are going to be replaced with chlorine. Okay, chlorine. So C double bond O Cl. The functional group will be C double bond O Cl. So this is an acid chloride. So here I have listed the functional group just now. So the table of functional group priorities for nomenclature, meaning that when you want to to decide the name of a particular organic compound, you have to follow this priority table. If in that compound it contains the functional group of carboxylic acid, maybe you have ketone, alcohol, so carboxylic acid will take priorities, meaning that the parent name will be carboxylic acid. Okay, the first always carboxylic acid at the top, whereas the least priority will be normal alkyl or alkane, or in fact the halogen that is attached, like haloalkane. Later we will see on the some of the example and also tutorial on how these priorities comes in. But you can always refer, I put this on in the earlier slide so that it is easier to refer. So before we begin on to the naming part, uh, you have to able to identify the types of carbon. Okay, so the types of carbon is actually you have to know to identify whether the carbon is either primary, secondary, tertiary, or quaternary. So here you have C over here. So this is the carbon that we are focusing on. So we are trying to determine this carbon, whether it is a primary, secondary, tertiary, or quaternary. So what is primary carbon? Primary carbon is bonded to only one other carbon, which is represented by this R group. So remember earlier, R can be any other alkyl, CH3, or in fact, it can be an aryl as well. So another carbon attached to one carbon. So that will be labeled as primary carbon. Okay, so normally they are written as take a pen. Okay, normally they are written as 1, okay, with the degree sign. Okay, the tiny circle. Okay, and then the second, for secondary carbon over here, this carbon is bonded to two other carbon, or in this case R group. Okay, let's say you can have CH3 on this carbon. Okay, you can have this CH3 over here. This one also you can have another CH3 for this R. So two other carbon. So that carbon in the middle will be considered as secondary, whereas for tertiary, when this carbon is bonded to three other carbon, you have 1, 2, 3. So tertiary. And quaternary, this carbon is bonded to 4 other carbons. Okay, so the limit, the maximum that the carbon can have is only 4. Okay, so it cannot have 5 bonds, 6 bonds, 7, okay, and so on. So why there is a limit of 4 bonds to carbon? That can be explained when you try to draw the Lewis structures, or you can also see on the hybridization. Okay, so carbon, the outermost shell, there are only 3 available orbital left, okay, for electrons to come in, okay, to be shared. So that's why this carbon can only form 4 bonds, okay, and the maximum is quaternary. So here an example. You have several types of carbon over here. This carbon number 5, okay, they are labeled as 1, 2, 3, 4, 5, 6, 7, 8. So these are actually based on their priority. Okay, for carbon number 1 over here, based on these rules, this carbon number 1 will be classified as primary. Okay, because it is bonded to one other carbon, only this one. Okay, and then the second carbon, so these are actually, what is this? It will be quaternary. Based on these rules, because this carbon is bonded to 1, 2, 3, 4 other carbons. Okay, and carbon number 7 and number 6 also will be primary. Carbon number 3 will be secondary. You have 1, you have 2, and then carbon number 4 will be tertiary. You have 1, 2, 3. Carbon number 8 will be primary as well because it is bonded to only one other carbon. Carbon number 5 also will be primary. So these identification for carbon being either primary, secondary, tertiary, or quaternary, you need to able to identify because it will be used throughout the reaction topics. Okay, because in the reaction topics, some of the intermediate will involve carbons either being primary, secondary, and tertiary, and it will affect the stability. So you need to know how to identify which intermediate is the which intermediate is more stable, so that which product will be formed. So let's try with this how to say test, or not that test, like exercise. So identify each of the carbon in the compounds below as either primary, secondary, tertiary, or quaternary carbon. So let's start with A. I will start first, and then B, C, and so on. You guys will try to answer them. So for A, so let's start with this carbon, let's say. So this carbon, I would say this would be primary because it is bonded to only this carbon over here. Okay, all of these structures are drawn in the skeletal form. Okay, so each of these how to say angle correspond to one carbon. So this would be primary. This one will be secondary because it is bonded to 1 and 2. Okay, this one, this carbon over here, there's another carbon, is tertiary because it is bonded to 1, 2, and 3. This one will be primary. This one also will be primary as well. Okay, because it is bonded to only one other carbon. So how about B? Volunteers. Siapa nak cuba? For B? Or I shall call who, yeah, let's see your name is Nadia. For B. Okay, how about this first carbon? What would you identify this as?
That one is BR is primary.
Okay, this one is primary. Okay. Nampak kan yang saya sedang
nampak.
okay. So this one?
This one secondary.
Secondary, okay.
Macam mana nak beza?
Sorry? Saya tak dengar.
Macam mana nak beza secondary ke?
So this would be primary. This one is secondary. Okay, why you said this one is secondary?
Sebab dia attached to primary and lagi satu.
It is attached to this one and also this one, right?
Yes.
Okay, how about this one?
Tertiary.
Okay, tak apa. Okay, kenapa you cakap tertiary? Why you say this one is tertiary? Tertiary means it is bonded to 3 other carbon.
Oh, this secondary
right. So it is bonded to 1 and 2. So this is also will be secondary.
Yes.
Yes, right. Okay, this one?
Secondary.
Secondary, confirm?
Confirm.
Confirm. Why? How many carbon it is attached to?
2.
Okay, 1. This one? Ada carbon kat sini.
That one primary.
No, this is bromine. This is bromine. So this would be primary. Kan tadi saya tunjuk kat sini kan. Like this, the first example I said like this one, this is tertiary. because it is bonded to 1, 2, and 3. Okay, this is not counted because this is already another type of atom, which is chlorine. Remember, the primary, secondary, tertiary, quaternary can only be determined if that particular carbon is bonded to other carbons. Okay, other carbons. Okay, let's try C. C. Aisyah, C.
C.
C. This carbon.
That one is primary.
This one will be primary. Okay. This carbon.
The second carbon is the secondary.
Secondary, correct. Okay, the last one.
The last one is primary.
Primary. Okay. So for D, Matan. Hello,
Yes,
are you there?
yeah.
Okay, let's try.
Primary.
This one will be primary.
Secondary.
Secondary, correct.
Secondary.
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 Okay, secondary.
Primary.
Primary, right. Okay, for E, I'll choose Tivia. Hello, Tivia? Are you there?
Sir,
Yeah?
yang E tu kan?
Yeah, okay.
Sekejap saya nak tanya. Yang garis panjang tu dia boleh jadi
Okay, this one.
ada functional group ke?
Tak ada.
Ke dia H je?
Oh, okay. This actually represents each of these is carbon, 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 carbon. Any functional group will be drawn. Okay, dia akan dilukis macam ni. Cl, OH, Br, chlorine. Actually, this one, I just want you to identify the carbon type. After this, saya akan ajar macam mana nak lukis structure ni. Actually, sepatutnya saya guna gambar lain, but I couldn't find any other example. But nonetheless, each of these ends over here represent one carbon. So one carbon, one carbon, one carbon, one carbon, one carbon. Unless that functional group is present, it will be drawn like this one: Br, OH, chlorine, I, chlorine. Okay, you need to draw any functional group. But if you see something like this in skeletal form, each of this end or angle will represent one carbon. Okay?
Okay, sir.
Okay.
Boleh ke saya nak try?
Boleh try. Tadi Tivia tak menjawab pun. Okay.
Primary.
Primary, correct.
Quaternary.
Quaternary, correct.
Primary.
Primary. This one. Yeah, this one
yang
is
tu pun
primary.
dua-dua quaternary.
This one.
Quaternary.
Quaternary. Quaternary ke?
Sebab dia attach dengan 3C
3C. 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon. So this one you said just now is primary. This carbon in the middle you said just now?
Quaternary.
Quaternary, correct. So this one?
Yang atas dia primary.
Primary, correct.
Primary juga.
Primary. This one?
Primary juga.
Primary, yes. So
Okay.
this 1, 2, 3 are actually the same. We can say that they are actually the same CH3, CH3, CH3. Okay, in the same environment. Okay, this one is also primary. So for F, any volunteers? Tivia, tadi tak ada pun. Dah left dah. How about Nivasini? Or class rep?
Yes, sir.
Yeah.
carbon is primary.
Okay, primary,
Carbon is secondary.
secondary, correct?
Third carbon is primary again.
Primary, yes. Okay, so primary, secondary, primary. Okay, so for G, H, I, and until L, we try to do it. Okay, later after class, the answer I will give during the next class. Let's see if you manage to get it right. Okay. Okay, it's okay, Tivia. So then we will go into this homolog series, okay, or homologous series. Uh, they are in the same functional groups, but they are differed by one specific portion of their molecules with regards to the number of carbon. So for example, alkanes with specific structural arrangement that differ by one methylene group, which is the CH2, form a homolog series given by this name. Okay, let's see. So the first four members of this alkane, they have this very specific name. For CH4, they are known as methane. Okay, this will be known as methane, only one carbon. And then if there are two carbons, CH3 with CH3, it will be known as ethane. And then for propane, when there are three carbons, CH3, CH2, CH3. And for butane, four carbon, okay, four carbon, CH3, CH2, CH2, and CH3. So the name over here are fixed like this. Okay, one carbon will be methane, two carbon ethane, three carbon propane, four carbon butane. So these are called as a homolog series. Okay, they are only differed by the number of these CH2 groups. Okay, and these homolog series are present for all types of functional groups. So we go to the first functional group, which is alkane. So this is the simplest and most common organic compound. Okay, it's very simple. It only contains carbon and hydrogen, and all of the bonds are single bond. Okay, all of the bonds are single. You will not find any double or triple or no functional groups present. So the general formula will be given by this CN, okay, number of carbon, and H2N plus 2, okay, where N is the integer 1, 2, 3, 4, okay, and etc. So let's say if there is one carbon, if you put in the formula, so C1, okay, normally 1 we don't write, so it's just C. So H 2 times 1 plus 2, so that will be 4. Okay, so there will be CH4. If there is two carbon present, for example, so we replace C2 over here, and then 2 times 2, which is 4, plus 2. So that will be 6. Okay, so C2H6. So, and you can try to replace to see, let's say if you have 50 carbon, okay, present, so there will be C50, and the amount of hydrogen can also be identified, meaning that 2 times 50, which is 100 plus 2. So there will be 102 hydrogen, okay, bonded to this 50 carbon. So the first three members of this class are represented by methane, ethane, propane, while the fourth is butane. So alkanes are inert, okay, chemically, meaning that they are not readily available to react. So you cannot, if let's say you mix it with other organic compound or other reagent, there won't be any reaction unless there is specific condition in which the reaction must have. Okay, and it is referred as paraffin oil, okay, or paraffins, which derive from the Latin word parum and affinis, which meaning lacking affinity or lack reactivity. okay, given that it is chemically inert. So this is an example of the C2H6 just now, which is the second in the homolog series, ethane. So the carbon atoms in the molecules are bonded to each other and also to 3 other hydrogen through a single covalent bond. Okay, so the maximum number of bonds a carbon can have is 4, okay, due to the valence, and the alkenes contain sp3 hybridized carbon, okay, which is in the second slide that I've shown earlier. So that is actually the representation for the hybridization, and the carbon atoms, carbon bond and also carbon hydrogen bonds are quite strong. So large amount of energy is needed to break them. Later you will learn in topic 7, which is the free radical reaction. So that particular unit is on the reaction of alkene. Okay. Then before we go into the naming itself, you need to know about this IUPAC. So the nomenclature or the naming rules are being given out by the International Union of Pure and Applied Chemistry. So this is a body, an international body, where they will meet up and devise rules and regulation so that the naming of this organic compound will be systematic, so that everybody will use the same naming so that you won't get confused. Okay, let's say like methane just now, if one country use methane and another use different names, so they will generate confusion. So what IUPAC does is it standardize the system in which organic compound are to be named. So the IUPAC name for an alkene will be constructed of 2 parts. Okay, the first is what we call as the prefix. The prefix is the name in front. Okay, and also the suffix, which is the N. So the prefix will tells you the number of carbon present in that particular alkene. Okay, so the first 4 number of carbon is given as meth, eth, prop, and also but. Okay, so in meaning that methane, ethane, propane, and butane. But the rest, starting from 5 onwards, it's more on the what you call Latin naming of being pan, hex, hep. Okay, like the one that you learn in I think polygon, like pentagon. Okay, they have 5 corners, so same like in pentane. So there are 5 carbons, and the suffix that you add, the end of the name, okay, will be A and E. So to indicate that the molecule is an alkene. So here we have the number of carbon. So the first 4 is already being given, being that methane, ethane, propane, and also butane. Okay, so meth meaning 1 carbon, ETH, eth here represent 2, prop is 3, but is 4. While for 5, 6, 7, 8, 9, and 10, it will follow the prefix, the Greek name. Okay, so penta, hexa, hepta, octa, nona, and deca. So these represent the number of carbon present throughout the whole compound. For deca, it means there are 10 carbons. Okay, and after number 10, there is also a system that you can follow. Okay, like 11, 12, 11 and 12, the name are slightly different, but starting from 15 onwards, it will follow the same prefix. Like let's say if you have 18, so that will be known as octadecane, for example. If you have 18 carbon, that will, you have to add 8 and 10, octadecane. But To find those very long alkyl chain is for your level, most is until up to 10. Okay, because the more complex structures are actually on like research level in masters or PhD, they normally try to synthesize those longer alkyl chain for different purposes. And then how to name the simple alkyl groups that are attached to the chain. So these chains refers to the longest backbone, meaning that if you have something like this, hexane for example, there are 6 carbon lying straight, okay, in one line, okay, in open chain. But then you have one CH3 group probably attached to the third carbon, for example, okay, to the third carbon. So that will make it as a substituents, okay, in that is no longer known as an alkane, but will be known as an alkyl groups. So the A and E suffix to the alkane name will be replaced by the YL in the naming groups. So example of some common alkyl groups is listed over here. So from methane become methyl, ethane it will be called as an ethyl, propane, propyl, okay, isopropane to isopropyl, and butane to N-butyl. Here, if you look at the group, all contain one dash line over here. So that dash actually means that this group needs to be bonded or connected to a longer chain, okay, to a longer carbon backbone. And then we also have common name, okay, beside IUPAC. Some of the organic compound like alkane, they have their own common name. So in common name, all isomeric alkanes have their parent name, and the names of various isomers are distinguished by their prefixes. The prefixes actually comes before. For example, the prefix N over here, okay, in front, when it is used in front, it indicates that all of the carbon are in one continuous chain, okay, in one straight chain. For example, you have CH3, CH2, CH2, CH3. So these are 4 carbons in one straight chain. So you can write it as N-butane, okay. But if you write it as butane, also that is acceptable according to IUPAC. Okay, but this is more on to the common name. And this one, another example, and pentane, where there are 5 carbon in one straight chain. Okay, the prefix iso, okay, is used to those alkane which have a methyl group CH3 attached to the second last carbon atom on the continuous chain. So what does it mean by the second last carbon, which is the second carbon? So let's say you have CH3, C, and then you have R. Okay, could be CH2, CH3, for example, or there could be 6 carbon over here. So this will be considered as the last carbon. This is second. So you have another CH3. And then this one, it is called as isopentane. So if you look over here on the second last carbon, okay, on this carbon, 1, 2, there is another CH3. Okay, if you look at this, what you call number of carbon, there are 5 carbon present, 1, 2, 3, 4, 5, hence the name isopentane. And this one, isobutane, because there are 4 carbons, 1, 2, 3, and 4. Okay, 1, 2, 3, and 4. But these, all of these follow common name. But if you want to give IUPAC name, you cannot write as isobutane, because this the longest straight chain will be 3 carbon, so that should be propane, and this will be considered as a substituents, okay, and you have to use the methyl just now. Later we will see. So prefix neo, okay, is used when you have 2 methyl groups from the second carbon. For example, this one, okay, this carbon, it is bonded to 2 CH3. This carbon is bonded to 2 CH3. You have one CH3 group, one CH3 group. This as well. So this is neopentane. There are 5 carbon, 1, 2, 3, 4, and 5. Whereas this one is neohexane, 1, 2, 3, 4, 5, 6. Okay, so this carbon, which is the second carbon, is bonded to 2 other metal groups, 1 and 2. This is not counted because this will be considered as the straight chain. Okay, so 1 and 2. So alkene isomers, okay, normal divided into normal and branch alkane, meaning chain isomerism. So for example, if let's say you have this chemical formula of C4H10, so 4 carbon with 10 hydrogen, it can be how to say arranged in a way that all of the carbon are positioned in a straight chain. You have C, 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 and C. Okay, so all of these carbon are in one straight chain like this: C, 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 and C. Whereas another way in which you can arrange these 4 carbon is these 3, okay, will be in one straight chain, while the other carbon will be as a substituent, okay, will be as branch, okay, will be branch like this. And here also, if you look on how the structure can be drawn, okay, first there are 3 ways in which you can draw the chemical structures of compound. One is by having these open structures. So I would say this is as the open structures in which you draw all of the carbon and hydrogen. So you draw C, 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 and all of the hydrogen. And then you have this simplified version in which that you straight away denote the number of hydrogen that is attached to that particular carbon. So you have CH3, CH2, CH2, CH3. So how do you know this carbon only contain 2 hydrogen, this one 3? So that is based on the open structure just now, like this one. The first thing when you want to draw is just connect all of the carbon first. Then only you fill out all of this hydrogen. Okay, because each carbon, the maximum number of bond is 4. It is already stated as a fact. So once all the carbon is there, so you just have to fill out the remaining of the hydrogen. Okay, and then you have this so-called skeletal form or skeletal structures that in the earlier example just now. So what each of these represent is 1 carbon. Okay, 1 carbon, 1 carbon, 1 carbon, 1 carbon. And the hydrogen is not drawn or it is not being represented. But by right, it is already know that, let's say, at this carbon, for example, in the middle, there will be 2 hydrogen. This one will be 3 hydrogen. This also will be 2. This one also, there will be 3 hydrogen. Okay, so in terms of how to say level of difficulty for beginners, okay, if you are still unsure or you're afraid that you're going to make mistake, opt for this one, meaning choose the open structure first. Okay, choose the open structures. Once you feel more comfortable, you can go to this simplified version, and once you feel that you are ready, you can go using these skeletal structures, because uh, most what you call a reference that you are going to find, not all will use these open structures like this. Okay, they will opt to use this skeletal form. So I hope later by doing the exercise and tutorial that is in the notes and tutorial I've already posted as well. So you can try to draw using this form first, and then after sometimes try to use this, and eventually try to use the skeletal form, okay, which is I think this is the most easier to draw, okay, because it looks like a zigzag, something like this. And this one, isobutane, okay, it is drawn using this line. It looks like there are 3 lines, but it actually represents 1 carbon, 2 carbon, 3 carbon, and also the 4th one is in the middle here. So the carbon in the middle actually represent 1 hydrogen. There is 1 hydrogen, but it is not drawn. Okay, it's not drawn. So another example, pentane. So this one contain 3 isomers in which you can draw a straight chain like this, a straight like this, or you can have 1 branch. You take one of the carbon and place it, could be here or it could be on the 2nd carbon, or you can have it like this, in which one of the carbon in the middle is bonded to 4 CH3 group. So as the number of carbon grows, so the more isomers that you are going to find. For example, like if you have 6 carbon, there are 5 ways in which the carbon can be placed or drawn, something like this. And if you look over here, once you have, let's say, 20 carbon, there are 366,000 more plus isomers. Okay, so the isomer is exponential. The more number of carbon that you have in your compound, okay, the more isomers that it can form. So that's why there is a need for the system of nomenclature, because to name this, let's say 3, it is quite easy, but once you have like 75 isomers, 366,000 isomers, this N, iso, and neo prefix are cannot be used throughout. Okay, so that's why we follow a certain system. So based on this IUPAC nomenclature, so this is how IUPAC tells us on how to name the organic compound, starting with alkane. So first you select and name the longest continuous carbon chain. So you have to find the longest chain that you find in the structure. Okay, so it is not necessary that the longest chain be written in a straight line. Okay, it may be straight or it may also be zigzag. Zigzag meaning that if you look like this, it may not be the one, the longest chain may not be straight like this. So it can be pointing downwards, for example. So always check, okay, the number of carbon present. So like this one, okay, you have a straight chain, so this is quite easy. So just count the number of carbon present, 1, 2, 3, 4, 5, and 6. So 6 carbon with no other carbon attached or branching. So straight away the name will be hexane, okay, according to the table earlier. And then second example over here, if you count the number of carbon straight like this, then you are going to find out there is 1, 2, 3, 4, 5, 6. Whereas if you take a corner, okay, 1, 2, 3, 4, 5 at here at this carbon, 5, 6, 7. Okay, so the longest chain, as said earlier, may not be straight, so it can be zigzag or branching. So 1, 2, 3, 4, 5, 6, 7. Okay, so always try to find the longest or continuous carbon chain. Like this, for example, if I take the straight one, so it will be 1, 2, 3, 4, 5, 6, and 7. If I start from here, 1, 2, 3, 4, 5, 6. So this one cannot. So always take the longest, G7. 1, 2, 3, 4, 5, 6, 7. Or 1, 2, 3, 4, 5, 6, 7. Also the same. Even if you start from this carbon, also it will give you 7 carbon chain. 1, 2, 3, 4, 5, 6, and 7. If you go this way also, it will give you 7 as well. Okay, so always try to find the longest continuous carbon chain. And then when there are two longest chain having equal number of carbons, select the one with the greater number of branches as the parent chain. So what does it mean? So if you look over here, this example give that the longest chain is 8. This one also give 8 carbon as the longest chain. But then again, this is stated to be wrong because there is only one branch. Okay, there's only one branching. Whereas for this, okay, there are two branching. You have one, you have two over here. Okay, so always select the longest chain that are having greater number of branches as the parent chain. Because if you start from here, it will be 1, 2, 3, 4, 5, 6, 7, 8. Okay, that is correct. Select the longest chain. But then again, the branching will be at carbon number 3 only. So only one. But if you start from this carbon, okay, from this one, 1, 2, 3, 4, 5, 6, 7, and 8, you're going to find that there are two branching happening at carbon number 2 and also carbon number 3. Okay, so select this structure over this one. So the name of the parent chain will be octane. Both will be octane, but this structure is correct. Okay, this structure will be correct. Okay, another example. This one is wrong, this one is wrong, but this is correct because it contains 4 branches. Okay, compared to this, only 2. This one, only 3. But for these structures, you can find 4 branches. Okay, 1, 2, 3, 4, 5, 6, 7, and 8. And the branching is at carbon number 2, carbon number 3, number 6, and number 7. Okay. And then rules number 3, name the chain, number the chain consecutively, starting at the end nearest to the substituent groups. Okay. And then designate the location of substituent group by an appropriate number and name. So the position number is mentioned before the name of substituents from which it is separated by a hyphen. So the complete name of the branch alkane will be written as one word. So what rules number 3, 4, and 5 said is that, so let's say you have these structures having 8 carbon. 1, 2, 3, 4, 5, 6, 7, and 8. And this one also basically the same thing, but you start counting from this side. Okay, 1, 2, 3, 4, 5, 6, 7, and 8. And this is considered wrong because rules number 3 said that number the chain consecutively starting at the end nearest to the substituent group. So what is a substituent group? Substituent is any branching that is available on the straight chain. So if you look at this structure, you have this branching at carbon number 6 for this one. 1, 2, 3, 4, 5, 6. But if you start numbering from this side, 1, 2, 3. So the branching is occurring at carbon number 3. So that is the branch or the substituents is having a lower number. Okay, so always start at the end nearest to the substituent groups. So the name for this compound will be 3-ethyl octane. Ethyl because this alkyl group contain 2 carbon. You have CH2, CH3. Okay, instead of 6-ethyl octane, so it will be known as 3-ethyl octane. This is also the wrong numbering of chain. So 1, 2, 3, 4, 5, 6, 7. Instead of this, the numbering should start from this side. So 1, 2, 3, 4, 5, 6, and 7. Okay, so the name should be 2-methyl heptane instead of 6-methyl heptane. So this one, the substituent group, okay, on how you are going to write it is you have to place the number or the position of that carbon. Let's say number 3 over here, it will be written as 3 and then separated by this so-called hyphen. So 3 dash, okay, or 2 dash Okay, and then the name of that substituents. So in this case, this is an alkyl group. So you just check the number of carbon for that substituents or for that alkyl. Whether it is 1, it will be methyl, 2 ethyl, if there is 3, it will be propyl, and so on. So it will be number hyphen the name of that substituents and the parent name, okay? Parent name of that alkane. Then rules number 6 state that when 2 or more different substituents are present, okay, just now only 1 substituents, but now if there are more than 2 substituents are present on the parent chain, you have to assign position number to each and list them in alphabetical order, okay, with hyphen. So the first thing, select the longest chain. Okay, here it is already stated that the longest chain is 7, but then for this one, the numbering is wrong because instead of starting from this side, you should start from here. So you have 1, 2, 3, 4, 5, 6, and 7. Okay, always try to give the lowest possible number to the substituents. Okay, so 1, 2, 3, 4, 5, 6, 7. So this is the correct numbering. But then in naming, okay, you don't give according to the numbers. Let's say here the substituents at carbon number 2 is methyl, but at carbon number 4 it is ethyl. So you don't write as 2 methyl 4 ethyl. Okay, that is wrong because that has to follow the alphabetical order. So between M and E comes first. E comes first, so it should be written as 4 ethyl 2 methyl heptane. Okay, 4 methyl 2 4 ethyl 2 methyl heptane. Okay, so correct numbering, correct name. And then number 7, if the substituents, okay, are having more than one, which is identical, so the prefix as such as di, tri, and tetra has to be used. Let's say there are more than one methyl group present, so you have to write it as either dimethyl for 2, tri for 3, tetra for 4. Okay, so for example, on this compound or this structure, you have 1, 2, 3, 4, 5, 6, 7. So this is the 7 longest chain. But then the substituents, you have one methyl group over here. Okay, and this one is ethyl group CH3, CH2, and this is also a methyl group CH3. So there are 2 methyl group present and 1 ethyl group. So once you start giving it the correct numbering, which is from this side, because always try to give the lowest possible number, 1, 2, 3, 4, 5, 6, and 7. And the substituents also have to be written in alphabetical order. So instead of 2, 5 dimethyl 4 ethyl heptane, it should be written as 4 ethyl E 2, 5 dimethyl heptane. So a question may be asked, this is D, it should come first before E, but the prefix di, tri, and tetra are ignored. So just focus on the name of that alkyl, original alkyl group, okay, being methyl, ethyl, propyl, and so on. Okay, even if there are 4, let's say tetra, so that also will be follow the M. Okay, it doesn't follow the prefix denoting the number of that particular substituents. And the 8th rules that you have to follow. So when branching occurs at an equal distance from either end of the longest chain, choose the name that gives the lowest number at the first point of difference. So example, you have 1, 2, 3, 4, 5, 6. Okay, and then from this side also 1, 2, 3, 4, 5, 6. So at the second carbon, if you follow this numbering, there is a substituent, same as well. Second carbon, there is a substituent. But if you follow this numbering, the second substituent will come in at carbon number 3. Unlike this, it will come at carbon number 4. So instead of 2,4,5 trimethylhexane, okay, or you have to choose 2,3,5 trimethylhexane. So the first point of difference is at carbon number 3 and carbon number 4. So why choose carbon number 4 when you can have the numbering at carbon number 3? So always goes for the lowest possible number, okay, for the substituents. Another example, here the substituents are listed as 22667 pentamethaoctane. So this is the correct name. Numbering start from this side. You have 1, 2, 3, 4, 5, 6, 7. So at carbon number 2. And from this side, it is 1, 2, 3, 4, 5, 6, 7, 8. So 23377 pentamethaoctane. So you have to see at the first point of difference. The first is 2, the same. But the second one, here you can have 2. But on this side, the number is number 3. So definitely choose this over this one. Okay. So always remember to give lowest possible number at the first point of difference. And in case the substituents on the parent chain is a complex one, okay, something like this, you have a branch, okay, a branching like this, and the branch itself contain another substituents of its own, okay. So what you have to do is the name of the complex substituents is given in brackets like this to avoid confusion with the numbers of the parent chain. So first write the number of the substituents. Okay, here is the substituents. It is at carbon number 5. And then you hyphen and put inside a bracket and do the same thing for the substituent itself. So you start numbering 1, 2, 3, and then at carbon number 1 and carbon number 2, you have this so-called methyl group. So 1,2-dimethyl propyl, because we have 1, 2, 3 in total, which is bonded to this long alkyl chain of 9 carbon, which is nonane. Okay, so 5 hyphen in bracket 1, 2 hyphen or dash dimethyl propyl nonane. Okay, so this is the last rules that you need to follow according to IUPAC. I know it sounds confusing. Later we'll try to do some exercise together. So how to draw the structure from given IUPAC name? So just now, structure is given, but how to name them? So this is how to draw when you are given a name. So first step would be to draw the longest carbon chain. So if you have this name given like 335 trimethylheptane, so don't draw from the front, you draw from the back. What does it mean from the back? You take note of the longest parent name, which is heptane. So you know in heptane, according to the table, heptane should contain 7 carbon. So straight away draw the 7 carbon. 1, 2, 3, 4, 5, 6, 7. So that's it. And then number those carbon as this one. In this case, you can start from here or you can start from this side. Doesn't matter. And then only you draw the substituents that is present. So in this case, there are 3 methyl group. Tri meaning 3, methyl is CH3. So 3 methyl group. And where does this methyl group situated? Okay, where you want to draw it. Okay, you draw at position carbon number 3 and also carbon number 5. So at carbon number 3, there are two carbon, whereas on carbon number 5, there is 1 carbon. Okay, then lastly, you complete the whole structures with hydrogen atoms. Meaning, once you have something like this, okay, by right, you should already know that this carbon should contain 3 hydrogen. Okay, because each carbon have to have 4 bonds each. So this carbon has 3 hydrogen this one 2 hydrogen, this one also 3, this one also 3, this one 0 hydrogen because it is already bonded to 4 other carbon, 1, 2, 3, 4. So no need to put hydrogen here. This one also 2 hydrogen, and this is 1 hydrogen, 3, 2, and 3. Okay, so 3, 2, 1 hydrogen, 3 hydrogen, and so on. Okay. Okay, now let's try. Okay, with the naming. Okay, we try together. Okay, the first example over here. Okay, write the impact names for this following compound. So what should we do is first look at the longest chain possible. Okay, try to find the longest alkyl chain that is possible. So start counting 1, 2, 3, 4, 5. Okay, here you find there is 5 carbon. And then if you start from this side, it will also be 1, 2, 3, 4, 5. So regardless, you start counting from here or from here, it will still be 5 carbon. So once you know that this is 5 carbon, you straight away know that 5 is pentane. So that is your how to say root name, okay, the parent name of that particular compound. So then what else is present? So you see there is one what do you call substituents. Okay, there is CH3 over here, one alkyl group. Okay, this alkyl group contain only one carbon, so this is CH3. So CH3 correspond to methyl. So you have methyl pentane, but where does the position of this methyl? So you have start counting just now. There are 5, and the number should be 1, 2, 3, 4, 5. So this will be at carbon number 2, and the numbering should not be from here. If you start counting from this side, so this will be 1, 2, 3, 4. So the methyl will be at carbon number 4. So that is wrong. So methyl will be at carbon number 2 because you will start how to say numbering from this side, 1, 2, 3, 4, and 5. Okay, so this will be known as 2-methyl pentane. Okay, 2-methyl pentane. So another example, let's see this one. Okay, slightly long shape here. So for this, you have to find out the longest chain. Okay, longest chain. So there are a lot of branching over here. So let's start. You can start anywhere. Okay, this is more like try and error. So you have to find. So let's say you start from here. 1, 2, 3, 4, 5, 6. So the straight one will be 6. Let's say you have 1, 2, 3, 4, 5, 6. This one also 6. If you start from this carbon, also you are going to end up with 6 carbon. From this side, 1, 2, 3, 4, 5. So cannot. 1, 2, 3, 4, 5, 6 as well. Same goes for this one. 1, 2, 3, 4, 5, 6. So the longest, now you know that it is at 6 carbon. So that will be hexane. So the parent name will be hexane. Then where to start the numbering from? From this side or from this side? So let's say we start from here. So if you give 1, 2, 3, 4, and 5. So 1, so this will be 2, 3, 4, and 5. Okay, 2, 3, 4, and 5. And then if you start numbering from here, it will also give 2, 3, 4, and 5. So it sounds, how to say, the same. Okay, the same. Meaning all of the substituents will be at carbon number 2, carbon number 3, carbon number 4, and carbon number 5. But now you have to look at the substituents that is present. So you have methyl group, and methyl group. How do I know this is methyl? Because this correspond to one carbon. When it becomes a substituent, CH4, it is no longer CH4, this is CH3, it will be known as methyl. Methyl, methyl, methyl. So there are 3 methyl. So the prefix that you should use is trimethyl. Okay, and then this one, the substituents is 1 carbon, 2 carbon. So instead of methyl, this should be known as ethyl. Okay, 2 carbon from ethane, when it becomes CH2, CH3, so this will be ethyl. So between ethyl and methyl, this will have more or less like high priority. So if you start from here, number 2 and number 3 will be for the methyl group. But if you start numbering from this side, this methyl will be carbon number 2, but the ethyl here will have the position at carbon number 3. But if you stay on numbering from this side, 1, 2, 3, say 1, 2, 3, 4, the ethyl end up being at carbon number 4. So to follow the IPAC rules, so the numbering should start from here. So 1, 2, 3, 4, 5, 6. So the name following alphabetical order between ethyl and M, E should come first. So it should be written as 3 ethyl, 3 ethyl, 3 dash ethyl, and then you have to put another dash with numbers of these 3 other substituents as well, which is carbon at carbon number 2, carbon number 4, and carbon number 5. So it should be written as 2, 4, 5, okay, 2, 4, 5 dash trimethyl hexane. Okay, so that is how the name should be written if there are more than one what do you call that, substituents. And here the second part is on drawing. So I think drawing should be slightly easier because you start draw the structure from the back, and then this one, the substituents based on the numbering, okay, and then you fill up with the rest of the hydrogen. Okay, we take a break for a while. Okay, now I want to ask you, for this part, I'm sure that there will be a lot of confusion. Betul, semua faham ke atau semua ada confused ni?
Sir,
Yes.
boleh saya ulang balik yang untuk yang macam